Hello friends, in our next lecture we are going to see a topic called as simulated annealing. Generally we call it as SEA. So this is simulated annealing. And we will be also seeing other algorithms like genetic algorithm and hill climbing algorithm. So let us go into the simulated annealing. Now generally why these kind of algorithms are useful is generally for the local search and the optimization. So already we have discussed something about PSO, that is particle swarm optimization. That is also for the local search space. So now in these optimization algorithms, how we have to do the local searches. First you see that keep the paths in the memory. So as when you travel using this algorithm, you just keep the path in the memory. So as you travel, you keep on storing all the existing path in the memory, or we generally call as a history. And remember alternatives, so search can backtrack. Solution to a path is a goal. So that means if you reach the goal, so that will be the solution. So till you reach the solution, you have to keep on tracking the existing path that you have traveled. So this is called as the previous searches. Sometimes the path may be irrelevant if only the final configuration is needed. So sometimes the existing path, whenever you travel, you need not remember all these things, but we need only the final configuration. One good example is the 8 queens. We can arrange 8 queens on a chessboard where all the queens could not meet each other. So that's how the way you can plan it. So in that case, the final configuration is what important. The steps what you put won't be necessary there. And IC design, final IC design will be important, and network optimization. So optimization of the computer networks, this is what important. So we have two things here, previous searches and the path may be irrelevant for some cases. Now here in the local search, use a single current state and move only to neighbors. So that means we have starting with a single state and move one after other to the next neighbors. Use little space. So generally when you travel, don't take bigger steps. So use small spaces or little spaces. Can find reasonable solutions in large or infinite state spaces for which the other algorithms are not suitable. So generally we can able to find the reasonable solutions in large or infinite state spaces for which the other algorithms are not suitable. Many algorithms may not be suitable to find it out, but using this local search we can easily find out the reasonable solutions. So in the local search algorithms, we have some algorithms called as hill climbing, simulated annealing, and genetic algorithm. These are the three algorithms we can have for local search. So two strategies for choosing the state to visit next. So if it is based on the next state visit, we have something called as hill climbing and simulated annealing. An extension to multiple current states. So existing current state, based on that we have genetic algorithms. So we are going to see all these things. So first thing is the hill climbing. Generally we call it the greedy local search algorithm. So it generates nearby successor states to the current state, pick the best and replace the current state with that one, and then it does the looping. So that means whenever you are climbing the hill, what you do is you take one step, go to the next step, like that it will go. So always when in the hill climbing algorithm, what you do is you only bother about the next step, what you want to take, what you want to carry, and if you have a best solution, you just take the step and then loop it. So that's how the way you just go for the hill climbing. So sometimes you have a dangerous path maybe coming up there, so you have to use a trial and error method and then try to find out the safest path, and then you can climb the hill. So same way the hill climbing algorithm is based on the successor states, not on the current state. So that is hill climbing, and based on this you can reach the hill. So here in the hill climbing search problem, we can see that we have a local maximum, plateau, and the ridges. So there are three methods available here. You can see here the local maximum here is, so just to climb the hill and you reach the maximum, then again you come back, then again you reach the maximum. So every time you reach the local maximum, a peak that is lower than the highest peak, so that the suboptimal solution is returned. So highest peak lesser than the highest peak, you just reach, this is called as the local maximum. And plateau is the evaluation function is flat, resulting in a random walk. So it is like a plateau means, so you just travel something like this, then you take a path here and then travel like this. So it is something like a plateau. Then ridges, slopes very gently toward a peak, so that search may oscillate from side to side. So it is like a ridge means, so you have to climb it to get the complete view of the peak. So that's what it's called as the ridges. So hill climbing search problem will have three things: either you reach with the local maximum, or the plateau, or the ridges. So here there are many variants of hill climbing. Start different hill climbing searches from random starting positions. stopping when a goal is found. So whenever a goal is found, you can just stop the process. So how do you go for a hill climbing is, so either you want to have a complete view or what is there from the top. So once you reach that particular top, you just stop because the goal is reached. Save the best result from any search so far. So whenever you just travel on a hill, just try to find out the paths further in future. The same path can be used for the other people who are coming and visit the hill. So that's how the way you have to find the best result out of it. If all states have equal probability of being generated, it is complete with the probability approaching 1. A goal state will eventually be generated. So that means once you finally found out everything there, it will be approaching the probability value of 1. As you know that the value of probability always will be 0 to 1. So you can able to find out the probability 1 if you reach the goal completely. Find an optimal solution becomes the question of sufficient number of restarts. So sufficient time, if you restart, then you can able to find an optimal solution. Suppose you are going for the first time, you reached your goal with after a lot of struggle. Then the second person, one who starts there, and he or she may able to reach the goal in a shorter duration of time. So likewise, the many restarts will make the find the optimal solution out of it. Surprisingly effective if there are not too many local maxima or plateaus. Okay, so that means if local maxima or plateau, if there are not too many things, then the optimal solution can be reached very easily. So next thing is the simulated annealing. It is based on the metallurgical metaphor. So what we do in simulated annealing is start with the temperature set very high and slowly reduce it. So annealing means, let's say a high volume of temperature, let's say 1000 degrees Celsius is there, and try to make the particle to get slowly it that let the temperature be reducing it, or you are just cooling down the temperature. That's the process of called as annealing. So how do you do the annealing process? Using a simulation. That's what we call the simulated annealing. So run hill climbing with a twist that you can occasionally replace the current state with the worst state based on the current temperature and how much worse the new state is. So here in the twist with the hill climbing here is, so the temperature set is very high and slowly reduce it. Here what says is with the worst state based on the current temperature and how much worse the new state is. So that means what? Suppose if the previous degree is 99.9 degrees Celsius and you want to cool down, the next set is 99.8 degrees and 99.7, like that you are just cooling down. So this process is called as the annealing process. So when compared to the hill climbing, so we are bothering about the next state, but here the next state is worse when compared to the hill climbing. That's what the simulated annealing do. So annealing is harden metals and glass by heating them to a high temperature and then gradually cooling them. So this is the annealing process. At the start, make lot of moves and then gradually slow down. So that means initially you have to make the lot of moves and then gradually you can able to slow down. So usually what we do is, usually if you go for a walking or a running, what happens, initial speed will be very high, but once you are about to reach the destination, if it is a long distance, then what you do, you just slow down and then just make yourself comfortable to have a slower movement. So that's what the process called as annealing. More formally, generate a new random new neighbor from the current state. If it is better, take it. If it is worse, then take it with some probability proportional to the temperature and delta between the new and the old states. See, suppose for example, every time when you are cooling down the temperature, 9900 to 99.8, if you feel 99.8 is fine, you just take it. If it is not fine, then you try to find a probability or a proportional to the temperature and then you have it. So every point of time you can reduce 0.5 degrees Celsius, or that way you can able to form it. So in that case 99.5, 99, 98.5, like that you can able to have it. So this process is called as the simulated annealing. So probability of a move decreases with the amount of delta E by which the evaluation is worsened. The second parameter T is also used to determine the probability. High T allows more worse moves and T close to 0 results in few or no bad moves. So close to T means, close to 0 means if the temperature is about to come to 0, then the result in no bad moves or few moves, only a smaller amount of moves, or there will be a no bad moves because it comes to 0. Schedule input determines the value of T as a function of the completed cycles. Okay. Now delta is nothing but the delta value. So that means if T equal to T minus delta E, that means what? So if T is 100 means 100 minus the delta is 0.5 means 99.5. If delta is 1 means 99. If delta is 2 means 98, 96, 94, like that every time. So based on this delta E value, it moves from one state to another state. Now this is what the algorithm of simulated annealing. So algorithms are very important if you feel that how the algorithm works. So we have a start and we have a schedule. So this is the function simulated annealing. So start equal to current. So the current state, the start state you give it to the current state for t equal to 1 to infinity. So the here infinity means till we reach the goal or till we reach the solution. That's what we infinity, because we do not know when we are going to reach the hill. So till the time we make it as infinity for assumption. Then schedule t, which is given to the schedule t here. So schedule of t, the time is given to t. If t equal to 0, then return current. That means what? If time equal to 0 means the time reaches 0, then return to current state. So again it will be starting from the beginning. Next, a randomly selected successor of current. So that means from one state to another state. So since it is hill climbing, that simulated annealing, you go to the next state. So delta E, value next minus value current. So we have a value next minus value current, the next value minus the current value. Suppose the next value, if I want to have 99.5, and what is the current value, so that way we can able to cool down. So that's what we have a delta E. If delta E greater than 0, then next is allocated to current. So next is allocated to current if delta E greater than 0. So that means if it is greater than 0, it is allocated the current state. Else current next only with the probability e power delta E by t. So that means we use a proportional value with a probability, and that value we can fix it for simulated annealing. So the algorithm is very simple. So we just schedule the t, and then based on the delta E value, we just moving to next state. If the state is acceptable, we accept it. If it is not acceptable, then with the probability value that can be allocated to current state and then move on. So that's how the way the simulated annealing algorithm works. Generally, annealing is a process by cooling down from a high temperature to a lowest temperature possible. We are just cooling down a particular metal or metallurgical operations. So that's what. How to do that in the simulation? If you don't feel that the next state what we expect is very high, then try to have a proportional probability value to allocate it. So this is the simulated annealing. The intuitions here is the hill climbing is incomplete. Pure random walk, keeping track of the best state found so far is complete but very inefficient, because hill climbing is always inefficient, because some people will reach at a lowest possible time, some people will take more time to reach, so it becomes very inefficient. So combine ideas, add some randomness to hill climbing to allow the possibility of escape from the local optimum, so that we can able to combine. The algorithm wanders around during the early parts of the search, hopefully toward a good general region of the state space. Toward the end, the algorithm does a more focused search, making a few bad moves. So for hill climbing, we can make a few bad moves towards the end. So that's what the intuitions of the hill climbing. So here the theoretical completeness is there is a proof that if the schedule lowers t slowly enough, simulated annealing will find a global optimum with the probability approaching 1. So that means there is a proof that if the schedule lowers t slowly enough, that means if you cool down the temperature slowly, simulated annealing will find a global optimum with the probability approaching 1. 1 means the highest probability possible. In practice, that may be way too many iterations. So in that case, it will go with a huge number of iterations, which includes more computation time. In practice, though, SA can be effective at finding good solutions. So generally, simulated annealing gives a good solution because the state is very slow and number of iterations are very high. So that means you will get a perfect solution out of it. So that's what we just call the simulated annealing. So third algorithm is something called as the genetic algorithm. So in this genetic algorithm, what it is based on the mutation, reproduction, like that. So it is like a cycle of a human cycle or an animal cycle, where how the reproduction mutation happens. So that is called the genetic algorithm. So the genetic algorithm, we have the algorithm like this. So we have a fitness function. So based on the fitness function, the genetic algorithm works. So push and pop means, so if it is a stack here, so if we are putting one element, we call that as a push. If you are removing one element, we call that as a pop. Okay. So similarly, genetic algorithm, we are pushing means we are adding one element into it, and popping means we are removing one element from it. Okay. So now we have the pop function, a fitness function, and the pop as a variable name. So new pop is empty. First I am making an empty. Then for I equal to 1 to size of the pop, then how many elements or how many kids or how many children or how many parent, whatever we call, that is the size of the pop. And random select, so x is you are selecting two things. So there are genetic algorithm, we are selecting x and y. There are two randomized selection here. Each one have a fitness function, and each has a each is belonging to the particular genetic group. Okay, so X is having one fitness function, that means X may be very powerful, Y may be a medium powerful. So we are going to mutate X with Y. So that is, so select X and Y, and child equal to reproduce X comma Y. That means what, X and Y can be reproducing and then produce one particular child. So this child will be having a property of the fitness function of X as well as fitness function of Y. So if small random probability child mutate child. So now next what happens is, if there is a random small probability, then mutate child will be given to child. So that means add child to new pop. So then what happens, the new pop is already empty. So this is been adding to the new pop here. So that means the expectation from X and Y, which is reproduction, which gives a child, that child is just mutating and that is allocated to the new pop. Now new pop equal to pop. So this will be what, the new pop whatever we generated, that will be given to pop until an individual is fit enough or out of time, return best individual pop according to fitness function. So we are going to generate genetic algorithm based on the number of children get reproduced based on these elements. In the next cycle what happened, this child become X and it will be mutated with another Y and it will generate another child here. This child will be given to the new pop. So likewise, based on the fitness function, the reproduction will be and mutation will be carried out in genetic algorithms. Now the reproduction X comma Y is, so first you find the length of X, then random number C equal to random number from 1 to n, return append substring X1 comma C, substring Y comma C plus 1 comma n. So now we can see here what it does is, so the substring of X, the random number from 1 to n, it is C and then it is 1, and here it is C plus 1 means the substring of Y. So this is the reproduction Y here, and n is the last number of the random number from 1 to n, and C plus 1 which is nothing but the random number plus 1. So this is how the way the mutation happened, and this is how the way the reproduction happened between X and Y. So this is what the genetic algorithm does. So genetic algorithm is based on the parent-child relationship. So if there is a family, there are only two people X and Y. So the two people X and Y, based on each fitness function, they reproduce and then they get one child. That child again will come into the loop, and that's how the way this genetic algorithm works well. So genetic algorithm can be solved using many problems, like for example, network optimization problems, cellular technology. So all the computational, electrical and the computer science problems can be solved using genetic algorithms, because genetic algorithm use hereditary, reproduction and mutation, which is very helpful for finding any optimization problems here. So when to use them? So genetic algorithms are easy to apply. Results can be good on some problems, bad on some other problems. So genetic algorithm cannot be good always giving a good solution. Sometimes it can give a thing. So that's why genetic algorithm mainly preferred for computer science and electronics related many optimization problems. Genetic algorithms are not well understood. So there was some complication on understanding the genetic algorithms. So in these lectures what we have seen is, we have seen the algorithms like PSO, then we have seen simulated annealing, then we have seen hill climbing, then we have discussed about genetic algorithm. So these are the four things that we can solve for the optimization problems. So each of these have a algorithm that can be solved for many application domains. So thank you friends.